Press your finger on the table, right now. Feel it push back. Solid. Real. Right? Wrong. Your finger and the table have never met. Not once. Not in your entire life. The force you call touch is something else entirely, and once you see it, you can't unsee it. Stay with me for 20 minutes. I'm going to walk you through what electricity actually is, the way Richard Feynman would have done it. With a roll of plastic wrap, a child's question, and an honest admission of what physics still doesn't know. Walk over to a light switch. Any light switch in your house. Now ask 3 questions a 6-year-old would ask. Question 1. When you flip the switch up, what travels down the wire to make the bulb glow? Most people will say electrons. That's what the textbook said. Hold that thought. Question 2. How fast is that thing moving? Most people will say the speed of light. That's also what the textbook said. Keep holding. Question 3. Is the wire actually hollow, like a tiny pipe, with little electron balls running through it? Most people will say yes. The teacher drew it on the board that way. The test wanted that answer. Here's the problem. One of those 3 answers is right. The other 2 are wrong. And the wrong ones are the ones almost everyone remembers, because a child asks better questions than a curriculum allows. Now, flip the switch off. Press your fingertip on the plastic plate. Feel the cool plastic push back against your skin. You are not touching that plate. I know. That sounds like a trick. It isn't. There is a measurable gap between your fingertip and that plastic that will never close. Not under any pressure your arm can produce. Not at the bottom of the ocean. Not under a hydraulic press. You have never touched anything in your life. Not your phone, not your dog, not the person you love most. We'll get to that. First, the wire. Grab a roll of plastic wrap. Any kitchen brand. Tear off a sheet about the length of your forearm. Now hold a ceramic mug in your other hand. Press the sheet against the side of the mug, drag it once, and let go. The plastic clings. It doesn't fall. A child watching you do that will ask the right question. Why? You didn't put glue on it. You didn't tape it. You dragged a piece of plastic across a clay surface, and the plastic disobeys gravity. Just for a moment. Just on the side of a coffee cup. Now tear off a second sheet. Hold one in each hand. Bring them slowly toward each other. They push apart. You can feel it in your wrists, the tiny shove, the refusal. 2 sheets of the same plastic, identical, repelling each other through empty air. What you just felt, the cling and the shove, is the same force that holds your body together. It's the same force that makes the floor solid under your feet. It's the same force that lets you read these words. There are exactly 4 forces in the universe. Gravity, the one a child notices first, is the weakest of the 4, by a margin we will name in a moment. 2 more, the strong and the weak nuclear forces, only reach across a distance smaller than an atom. That leaves 1. Electromagnetism. That's it. Every push, every pull, every soft pressure of a sweater against your shoulder, 1 force. Feynman wrote this down in the Lectures, Volume 2. He didn't dress it up. He just said, it's all the same thing. We still don't know why charge exists, but we know what it does. In a moment, I'll show you how strong that margin actually is. The number is, it's almost a joke. Here's the joke. Take 2 electrons. Hold them about 1 inch apart, roughly 2.5 centimeters. The distance between 2 of your fingertips when you make a pinch. Gravity is pulling them together. We all know gravity. It's the force that holds you to the floor. It dropped the apple on Newton. Electromagnetism is pushing them apart, because they carry the same charge. Same sign charges repel. Now ask the child question. By how much does the push beat the pull? Pick up the plastic wrap again. Hold 1 sheet in each hand. Feel the tiny shove between them. That shove is winning. It's winning by a factor of 4.17 times 10 to the 42nd. Write that down as a number, and you write a 4, a dot, and then 41 digits. 42 zeros after the 4, if you write it the lazy way. It's a number that doesn't have a name in any language a child speaks. It barely has a name in any language a physicist speaks. That is the margin between the force that pulls the universe together and the force that pushes plastic away from plastic on the side of a coffee cup. The coffee cup wins by 42 zeros. And here is where I have to be honest with you. We can measure that number. We can write the law that produces it, Coulomb did, in 1785. But we cannot tell you why charge exists at all, Dirac asked. Feynman asked. We're still asking. So now you know how strong the push is. The next question is the one that breaks the textbook open. What, exactly, is moving? Walk over to a lamp. Look at the cord running down to the outlet. 3 feet, maybe about 1 meter of copper inside that plastic sheath. Flip the switch on. The bulb lights up. Instantly. You don't wait. There's no delay you can feel. Now ask the child question. If the bulb lit up the instant you flipped the switch, then something traveled down that wire faster than your finger could move. Something almost the speed of light. The textbook told you it was electrons. Look at the stopwatch. 3 feet of wire. 1 meter. If an electron started at the switch when you flipped it, when does it reach the bulb? About an hour. Sometimes longer. That isn't a typo. Inside a normal household copper wire, under normal current, the electrons crawl. Not run. Not race. Crawl somewhere between 0.04 of an inch per second and 1 millimeter per second, roughly 1/10 of a millimeter to 1 millimeter per second. A garden snail moves about 1 millimeter a second. Faster than this, often a lot faster. So the snail wins. Which means, and this is the moment the textbook breaks open, the electron is not what's traveling at light speed down your lamp cord. It can't be. It barely moves at all. Something else is racing through that wire. Something the electrons are only carrying a message about. And here's the fair part. The textbook isn't lying to you. It's averaging. Electrons move through the wire is true at the timescale of a year. It's wrong at the timescale of a second. Your teacher was holding a true sentence the wrong way around. So if the electron isn't what's moving at the speed of light, what is? The answer to that question has a name, and a date, and a chalkboard. The name is James Clerk Maxwell. The date is 1864. The chalkboard was in London. Maxwell was 33 years old. He had spent 7 years pulling together everything anyone had ever measured about electricity and magnetism, Faraday's experiments, Ampere's law, the work of Gauss, the quiet observations of a dozen others, and he had a question a child would ask. Are these the same thing, or two things that happen to look alike? Picture the chalkboard, a foot of slate about 30 centimeters across, Maxwell standing in front of it, chalk in one hand, the wrong end of an answer in the other. He wrote 4 equations. Not 400. Not a textbook. 4 lines of chalk. 1 year later, he submitted them to the Philosophical Transactions of the Royal Society. The paper was called A Dynamical Theory of the Electromagnetic Field, and buried in those 4 lines was a number nobody had asked the equations to produce. The number was the speed of light. Maxwell did not put it there. The equations did. He was not dressing it up. He was writing what he saw. And if Maxwell wrote it down, and you never saw it in school, that wasn't your fault either. The test was busy with batteries and bulbs. The chalkboard waited. So what is it, then, that the chalkboard says is moving at the speed of light down your lamp cord? Watch your lamp cord again. Picture the copper inside the plastic. Now stop picturing the electrons. Picture the space around the wire, the empty space, the air, the plastic sheath, the thin, invisible region wrapping the copper like a glove. Watch the field lines. Not the wire, the field. The wire is a railing. The runner is the field. When you flip the switch, you don't shove electrons down a hallway. You change the electric and magnetic field along the outside of that copper. That change races down the cord at somewhere between 0.5 and 90% the speed of light, 186,000 miles per second. At its top end, roughly 300,000 kilometers per second. The electrons inside? They are the messenger's messengers. They jostle, they nudge each other a fraction of a millimeter. They carry the message about the field. But the message is the field. The field is the signal. The textbook quietly swapped 2 things and never told you. The runner was never the electron. The runner is the field. The wire is just where the field is allowed to run. And here is the honest part I owe you. Physicists still argue about lossy dielectrics, the messy materials where the field loses energy to the wire and the plastic in the air. The 0.5 to 90% figure is the average. The full answer depends on what's around the wire. The textbook answer is the average. The full answer is messier. Once you see that the wire is a railing and the field is the runner, one more thing breaks open. The thing you've been waiting for since the start. What touch actually is. Put your finger on the table in front of you. Press down. Feel it push back. Now ask the child question one more time. What exactly is touching what? The answer is, nothing is. Bring the camera close. Closer. Now look at the gap. If you could zoom in on the place where your fingertip meets the table, you would see something the textbook almost never says out loud. There is a gap, a real, measurable gap, about 1 nanometer wide, roughly 400 millionths of an inch. It never closes. Not when you press harder. Not when you slam your hand down. Not at the bottom of the ocean. The outer electrons in the skin of your finger and the outer electrons in the surface of the table have to stay apart. Two of them cannot share the same quantum state. That is not a suggestion. That is a rule the universe writes in chalk and refuses to erase. The name of the rule is the Pauli exclusion principle. The man who wrote it down was Wolfgang Pauli in 1925. Feynman taught it in the Lectures on Physics, Volume 3, Chapter 4. He used a child's language for it. So will I. The universe says no. Between every two electrons that get close enough, the universe says no and pushes them apart with the same electromagnetic force you felt in the plastic wrap. You have never touched anything in your life. Not your phone. Not your dog. Not the person you love most. You have felt the force. The force is real. The contact never was. And if no one ever told you that that wasn't your fault either, Pauli wrote it down. Feynman taught it. The curriculum quietly chose batteries and bulbs. So that is 3 of the 4 forces accounted for in everything you have ever felt. There is one more force in the universe, and it is the one nobody, not even Feynman, ever solved. There are 4 forces. We have named 3 of them in the last 20 minutes: the strong nuclear force, the weak nuclear force, and electromagnetism. The standard model of physics has those 3 written into one rulebook. 3 of the 4 play by the same chalk. The 4th is gravity. Gravity is the holdout. We have no working theory that unifies gravity with the other 3. Not in the standard model, not after 100 years of trying. Feynman tried, Dirac tried. The smartest people alive right now are still trying, and Feynman would have said, "Don't hide that. Tell them." So I am telling you, we can show you how electricity works. We cannot tell you why charge exists, and we cannot tell you why gravity refuses to come into the room. So here is what is left. The truth is simpler than the textbook, and it starts with what you were told about water. Here is the sentence the textbook gave you. Read it slow. Electrons travel down the wire and carry the electricity through the pipe. That sentence has 3 words doing damage. Travel, carry, pipe. Electrons do not travel down the wire. We watch them. They crawl at less than a millimeter a second. A garden snail beats them. Electrons do not carry the electricity. The field carries it. The electrons are the railing. The field runs along. We watch that too, half to 90% the speed of light, in the empty space wrapped around the copper, not inside it. And the wire is not a pipe. A pipe is hollow. A wire is solid. There is no inside for the electricity to slosh around in. Grab a wooden skewer. Slide a single bead onto it. Push the bead from one end. The bead doesn't travel down the skewer. The skewer doesn't get hollowed out. The bead nudges the next bead, and the next. And the message, the push, runs along the skewer at the speed of your hand. A foot of bead stick about 30 centimeters, and the push lands on the far end almost before you feel it leave your finger. That is closer to what electricity does than any pipe of water ever was. So here is the reconcile. If you got the water analogy on a test in 1998, that wasn't your fault. The test wanted that answer. The textbook wanted that answer. The grading rubric wanted that answer. The system was busy with batteries and bulbs. But you know better now. You have a snail, a railing, a runner, a chalkboard from 1864, and a bead on a stick. You have the truth in your hand. There is one more layer underneath this, the one Feynman built his Nobel Prize on. Under the field, there is one more layer. The layer Richard Feynman built his Nobel Prize on, in 1965. The field tells you what happens at human scale. But under the field, the universe keeps the books in light speed, in particles, and in trades. Draw 2 lines, 2 electrons, coming toward each other. Now draw a wavy line between them, a single photon, showing up out of nowhere, getting passed across, and vanishing. That wavy line is what push actually is. Down at the smallest scale, when 2 electrons repel each other, a photon shows up, gets traded, and vanishes back into the field. A virtual photon. Not a beam of light you can catch, a bookkeeping particle the universe uses to settle the account. Feynman called this quantum electrodynamics, QED. He wrote a book about it in 1985, for people who never took a physics class. He drew the wavy lines himself. And here is the part you tell people at the dinner table. QED is the most precise rulebook anyone ever wrote. We have tested it against reality to 1 part in a trillion, close enough that across the diameter of New York, about 34 miles or 55 kilometers, you'd be wrong by less than the width of a human hair. This is the rulebook your fingertip is reading right now. So, let's bring it home. Let me give you the whole thing back, in 4 sentences. 20 minutes ago, you walked over to a light switch and asked 3 child questions. And the test wanted answers a child would never have given. You picked up a roll of plastic wrap, felt the cling and the shove, and met the one force out of 4 that holds your body and your floor and your phone and your sweater and the person sitting next to you together by a margin of 42 zeros over gravity. You watched the electron crawl through copper slower than a garden snail, while the field raced down the outside of the wire at the speed of light, and you stood in front of a chalkboard from 1864 where 4 lines of chalk produced that speed without James Clerk Maxwell putting it there. And then you pressed your finger on a table you have never touched, not once, not in your entire life, traded a wavy line between 2 electrons in the most precise rulebook anyone has ever written, and you heard 3 honest admissions in a row. We still don't know why charge exists. Physicists still argue about lossy dielectrics, and gravity, after 100 years of trying, will not come into the room. That is what electricity is. That is the way Richard Feynman would have done it. And here is the part nobody can take from you now. You can teach this to anyone, with a roll of plastic wrap, a child's question, and a chalkboard, and you can tell them the honest part too. That is the whole job. Next time, the one thing Feynman never finished, the one force that still won't come into the room. We still don't know why charge exists. Good night.